All right, so what I'm going to be covering right here is basically just a little bit overview of Ohm's law and a little bit of power law. These are both what I call Ohm's law circle, power law circle. I'm going to get into just a little bit about the equations, just to give you a summary of that. And then also I'm going to make sure that we understand the different types of units we use, like kilo, meg, milli, and micro. And then also I want to talk about finally the three parts of a series circuit. So first of all, let's discuss the Ohm's law circle and the power law circle to start out. So the Ohm's law circle, what we have here is V, I, and R. So we can look at this horizontal bar as a division sign and then the vertical bar as a multiplication. That's how I came up with these three equations. So V is equal to I times R, cover up V, and you get I times R. Likewise, if we cover up I, we got V over R, and that's division, so R is divisible into V. And likewise, if we do R, I get V over I, same thing. So this is the power law. Remember, power is, and so we have to look at a couple things here. Power is in watts, and this is energy. So V is in volts. And I'm going to actually explain to you that this E right here is the same as V. And there is a reason why you use E instead of V, and that basically details in 103, goes into some detail in 103, which is electromotive force. So we have V is I got times R, so let's see what I want here. Okay, I got powers in watts, see VIR. I'm going to start over because I don't like what I just did. This is baloney. What I'm going to go through here is the basics of a circuit. It could be a series circuit. I'm going to use actually a series circuit, but it could be any circuit. And what I'm going to talk about, Ohm's law and power law, and the basic fundamentals on here, could be applied to the three basic circuits. That's series, that's parallel, and combination. Those are the three types of circuits we actually have that are out there. So if you can follow Ohm's law and power law and apply them to those circuits, you can pretty much come up with any of your answers that you need. So I'm going to start up on top with the Ohm's law and the power law circle. So basically in the book, any DC fundamentals book, you have a Ohm's law, you got V, and then you get I and R. So V is volts, I is current. So let me put that down. I is equal to the current, and that's measured in amps. And we actually use millis and milliamps or microamps here. R is resistance. And that is in ohms. And we do have the omega symbol. And then V is in volts. And what we're going to do is use E instead of V in the power. So just keep that in mind. So these basic equations, how I came up with them is this horizontal line is like a division line, and this vertical line is like a multiplication. So if I actually cover up V, I'm looking for V, I got I times R. Likewise, if I cover up I got V over R, or R is divisible into V. So that's how you came up with the standard three standard equations that we use for Ohm's law. Power law, there is approximately, I think, 9 equations that you can use, but the fundamental ones are the three top ones here, and then by substituting some of the Ohm's law into here, you come up with such as P is equal to I squared R. Similar, so what we have, remember that E is interchangeable with V, so you have P, I, and E. So if we have P, you come with I times E. Likewise, if you cover up I, you got P over E. Remember that when we're looking at power is in watts, and that's the energy. And usually we have in milliwatts or in microwatts, or even sometimes we get into larger industrial equipment, or even some home appliance systems, you get into the watt system of it. So it can be even kilowatts. So keep that in mind. So power is actually watts is energy. And remember, energy is heat. So I could put that down for you as heat. So that could be actually heat. So before we get into solving this basic equation, I want to make sure that we understand some of the basic foundations of a circuit itself, a series circuit. So this is what we call a series circuit. And I'm going to start out with this one. Eventually, we'll bring ourselves into parallel and combination later on. So a series circuit, basically you have a DC power source, and this is a single cell battery. But you notice that I use the single cell battery to represent a high voltage. In a single cell battery, we take just a quick glance at this. You have the positive and negative down here. And this is actually a 1.5 volts. But, you know, if we decide to make this 20 volts using multiple cells, this thing would be stretched out. So, again, what we do in industry is just use a large bar and a small bar, horizontal bar, and we represent that as a DC battery, and we can label it whatever voltage we want. In a series circuit, we actually have multiple loads. These resistors are considered loads. So it could be anything. These loads could be any device that we have. It could be a toaster, it could be a computer, it could be you. Don't let it be you, but it could be anything. So in this case, we're just using standard carbon wound resistors. We can use some ceramic resistors. We could use anything we want in the lab. So in this case, what I have here is to identify this as a series circuit, I have my polarities, positive, negative, positive, negative, positive, negative, because I keep going in a circle. This is called conventional current flow. I already talked a little bit about this, but I'm just going to go a little deeper on this. So again, as current is flowing through the circuit here, it hits this first resistor, speed bump. Well, once it gets a passage, it picks itself back up to full speed, and it keeps going through. So from the readings, we know that current is the same, so we can say that current is the same throughout the circuit. So if we have, if that's true, the current at this point, the current at this point, and likewise the current at this point will be all the same. So let's break away from this just a little bit, and let's talk about kilo, meg, milli, and micro. Because these are the units we want to use, kilo, meg, milli, and micro. And kilo is 10 to the third, which is 1,000. Meg is 10 to the sixth, which is 1 million. But look at this, milli, these are lowercase, these are uppercase. These are lowercase, so that's how you can tell. And also we're using a negative exponent. So milli is 10 to the minus 3 is 0.001. Micro is 10 to the minus 6, which is 0.000001. So it's 1, 2, 3, 4, 5 zeros and a 1. And that's how we get micro. So if we actually look at this and say, okay, kilo, we look at kilo, the abbreviation is usually a K. It is a K. If we look at meg, that's capital M. Likewise, if we say milli, that's going to be the small m. And then micro, well, we're not going to use the small m because it's already been used. We're going to use this symbol. That's a mu. That's the mu. So let's first find the total resistance in the circuit. We know that in a series circuit, because it's in a series circuit, it's an additive circuit, we can find our total by having our total is equal to R1 plus R2 plus R3. And we want to use the units. We want to use the units. So for kilo, we're going to use K, meg, whatever it is. So in this case, we're going to have 100 ohms plus 470 ohms. And I'm going to actually change this to 1.6, just so you can actually see this, 1.6K. So we can actually use the kilo. And I'm going to have 1.680K ohms. You notice I'm using the omega symbol for this, from ohms. So if I add all these up, I'm going to actually kind of come up with, so I use my calculator, and I'm just going to use my calculator, 100 plus 470 plus 1.680 exp to the 3. So that's, remember, K is positive, so I'm putting 1.68 times 10 to the third power. I come up with 2,250 ohms. Well, we don't want to just write it like that. We want to use the standard notation on this. We're going to be using some standard notation. So we're going to write this as 2.250K ohms. Why? Because my decimals right here. I move back 3. 1, 2, 3. There it is. 2.25K ohms. So now let's get something with milli. I know that the current in here is going to be a milliamp, so let's find I total. Voltage drops using the same circuit we did before. What I want to do is find the voltage drops of VR1, VR2, and VR3. But there's two ways to actually come up with these voltage drops. One is to use the IR relationship. That's your IR, that's your current times the resistor. In this case, I took 8.89 milliamps times 100 ohms, and I came up with 0.889 volts. Or I could have said this is 889 millivolts because I moved the decimal over 3 places to the right. Likewise, VR2, same thing, 8.89 milli. Remember, the milli is 10 to the minus 3. So when I put that in the calculator, I have to put in 8.89 exponential minus 3 exp, or 10 to the minus 3, times it by your resistor value, 470, and then I should come up with 4.17 volts. Likewise, the last one is the same way. Now, what's interesting here is you take VR1, VR2, and VR3, and you add them together, we should obtain close to 20 volts. And that's called Kirchhoff's voltage law. Kirchhoff's voltage law states that if I take the voltage total and I subtract it off of all my voltage drops, I should become close to zero. The other way we can actually do this is the way we call the voltage divider rule. And the voltage divider rule basically states that I could take the voltage across, this is saying the voltage across whatever my resistor, that's what the X means, is equal to the resistor I'm looking for, that's Rx. So let's say it's the R1, so I put 1 right here, over R total, and I take it and I multiply it by voltage total. So this is a ratio of that resistor I'm looking for to the total resistance times by voltage total. I did just VR1 just as an example. So I take 100 ohms and I divide it by the total resistances, which is 2.250 k ohms, and I multiply by 20, which gives me 0.8880 volts or 880 millivolts, which is the same thing as this one. Actually, this should be 889 millivolts. So this one, if I did this correct, it should be 0.889 to keep everything consistent up there, or 889 millivolts. So if I did this, I would say, if you gave me it this way, I would be fine with it. I would just say watch your third decimal place, etc. on that. So I hope that explains that a little better. Now powers. Remember, power is the amount of energy, heat, watts. Again, I have many equations I could do to find the power. So the first thing is you want to find power total. That is equal to I times E total. E is the same as V, so I total times E total, so it's pi. So that's 889 milliamps times 20 volts. Then I get 0.1778 watts of power, or 177.8 milliwatts. Why? Moving the decimal to the right. Now, PR3, I use the I squared R equation. So I took 889 milliamps, squared it, and I multiplied by that R3, and I came up with 132.8 milliwatts of power. So I could find it other ways. I could find PR3 by doing, let's see, I could use, I'm looking for power, I could use I is equal to P over E. Excuse me, not that one. I could use I times, I could use I times E, sorry. So P, I could find PR3 is equal to the I times the E. When I use the E, I have to use ER3, and which came up with the same one up here. Now, similar, you can actually take all the powers, add them together, and you should come up with power total. Hope that explains a little more detail of how to be using the prefixes and solving for different powers of voltages.